Weber. I'm a trainer for Eiffel software. In this presentation, I hope to give you a feel for how Eiffel compares to the UML. Comparing these two technologies is a little tricky because although they have some common goals, there are many important differences, both in their intents and their capabilities. As you almost certainly already know, the UML has become the favored notation for many of today's system developers. The UML specification is, by the admission of its authors, a large and complex thing. Like many of the people who actually use UML, I don't have a complete understanding of all that's there. But I should be able to give you a general feel for how it relates to Eiffel. We'll look first at how the UML was developed and why it's an important contribution to software engineering. Then we'll look at some things that the UML has in common with Eiffel and some important ways in which they differ. Let me talk some about the nature and origin of UML. In the late 1980s and early 90s, people who had been pursuing object-oriented technology as a potentially promising programming discipline began to think of how our view of analysis and design might be changed by the presence of this same technology. For many software engineers, myself included, it was a very exciting time. OO was a fresh and more powerful way of thinking about the software construction tasks that we had been doing using essentially the same discipline since the structured programming revolution of the 1970s. So over a period of a few years, many papers and books were published, many classes and seminars were taught, and many methods and notations emerged. Although all these efforts looked different and each had its own focus and background, the central theme of OO ran through them all. I remember thinking that some of the graphical notations looked a lot like entity relationship diagrams expanded with operations and inheritance. Some looked like a form of state diagramming, and others appeared different from anything I'd seen before. So there were lots of OO methods, and Eiffel is one of them. The books of Bertrand Meyer, published since 1988, describe the Eiffel methodology and language. All these authors and methodologists had somewhat diverse backgrounds. They included typical corporate and government IT, process control and real-time computing, computer science research, very large system development, formal methods, simulation, and other areas. And usually the methods and publications reflected the backgrounds of their authors. So it's no wonder things were a bit muddled. I remember one author comparing OO to relational database, that is, in their roles as promising technologies. This person said that OO will never be as cleanly defined as relational database because where relational database had one primary theorist, Dr. Codd, upon whose work all relational products were based, OO had no such single respected guru. And maybe there's some truth there. But as we'll see, for better or worse, UML is an effort to bring together and add some formality to many of these diverse views of object orientation. Well, as the mid-1990s approached, some engineers and methodologists began to feel the urge to provide some sort of standardization across methods and notations. Grady Booch and Jim Rumbaugh began to collaborate about merging their respective ideas, and the result was the beginning of UML. Later, Ivar Jakobsen joined the group. By 1996, the Object Management Group, or OMG, became involved as a standards organization. OMG is an open membership, not-for-profit consortium which specializes in producing standards for the computer industry, which it calls specifications. I'm certain that the folks at OMG would point out that there are important differences between a standard and a specification. But my intuition tells me that you might not be able to tell much difference if your boss smacks you over the head with one. So OMG is a computer industry standards organization, a lot like W3C, ECMA, OASIS, CompTIA, ANSI, ISO, and numerous others. Someone once said that a beautiful thing about standards is that there are so many to choose from. Well, apparently the same thing applies to standard organizations. Anyway, when the OMG became involved, the UML went through some pre-release versions with lots of wrangling and heavy thought by the methodologists and consortium members involved. Concepts present in other methods and notations, including Eiffel, were added along the way. OMG adopted UML version 1.1 as a specification in November of 1997. Work on the UML continued through various one-point releases and an eventual standards endorsement from ISO. As I'm putting this presentation together, the current version of UML is version 2.0. This latest version hopes to fix some problems in previous versions, plus support model-driven architecture, the official OMG approach to model-driven development. Let's take a quick look now at the four major components of UML 2.0. The UML is managed in four parts: infrastructure, superstructure, object constraint language, and diagram interchange, each with its own specification document. I should point out now that if you're not already familiar with the UML and/or you want to learn more, at the outset you should stick with one of the many available UML books or online tutorials. The official OMG documents are likely not for you. Believe me, this is not wimpy reading, and although the emphasis is clearly on the technical, some of the grammar betrays the need for a bit of serious proofreading. Of the four parts, only two are of much interest to typical software developers: the superstructure and the object constraint language. The infrastructure defines some building blocks upon which the rest of UML is based. The diagram interchange defines a format for exchanging UML-compatible documents. The superstructure is the definition for 13 different diagramming types. Each type of diagram is classified as depicting either structure, behavior, or interaction. The object constraint language allows the UML user to place constraints on the elements of a model. So this means that UML models can contain preconditions, postconditions, and invariants, much like those in Eiffel. So one of the important achievements of the crafters of the UML is bringing together and rationalizing, if you'll forgive the pun, a group of diverse sets of ideas and notations. Despite being criticized for its complexity and inconsistency, the fact that all these notations are as well defined as they are and fit together as well as they do is amazing in itself, and a credit to the UML designers and the OMG. Well, that's a little bit about where the UML came from and what it's made of. Now let's see how it differs from Eiffel. One of the biggest differences between the UML and Eiffel is that UML is a language, or notation if you will, and Eiffel is a software development method. But having said that, let's take a closer look. Eiffel is a method, a recipe for building high-quality, purely object-oriented software. It also includes a notation, the Eiffel language, with which to express the products of the method. The UML claims to be only a language. However, it's difficult to talk much about the elements of UML without associating it with a certain class of development methods. For example, the class diagramming in UML allows depiction of inheritance, a cornerstone of object-oriented thinking. All the primary contributors to the UML were dealing with the issues of object technology when their contributions emerged. So it's pretty clear that the UML is intended to be used in conjunction with one of the object-oriented development methods or processes. Even though parts of it would certainly be applicable in the absence of OO, and as we'll see later on, parts of the UML may actually work counter to the goals of OO. The UML notation is mostly graphical, although some parts are textual. The Eiffel notation is 100% textual. However, parts of an Eiffel model can be viewed and edited in graphical form. The role of the UML is limited to analysis and design, but there are UML-compliant tools that will do some code generation from a UML model. Code generation, at least in OMG's latest meta-object facility, is done in two steps. One step in model space to go from a platform-independent model to a platform-dependent model, and a second step as the project goes from model space to code space. Eiffel is targeted to the entire life cycle and is seamless and reversible. An important difference between Eiffel and the UML is that there's never any code generation from an Eiffel model, because the model is in the code. You use the same language and tools from analysis through implementation, constantly increasing the level of detail and adding relationships as you go. Once you've achieved sufficient detail, the product of your efforts will compile into a running system or a set of software components. Now, whenever I'm speaking to an audience face-to-face and I say that in Eiffel the model is in the code, I usually see some faces go blank, and a few pairs of eyes will glaze over like 4-day-old trout at the fish market. This is understandable, because these people are trying to imagine what it would be like to use their programming language of choice to record and communicate the products of analysis and design. And that wouldn't work very well with any mainstream programming language other than Eiffel. So if these people are unfamiliar with Eiffel, then they'll be understandably skeptical as well, which is okay with us. Converted skeptics make great evangelists. Back to the point. The Eiffel language is designed as a notation for the Eiffel method and designed to express the products of all development phases in a way that's easily interpreted by the target viewer. Pardon me if I say just one more thing about that expression, target viewer. Often when we point out the clean, elegant syntax of Eiffel as an advantage over other programming languages, developers tell us, well, it doesn't matter that my language uses a lot of special characters and arcane structures. It's the way that things have been done for years, and good programmers are accustomed to working this way. Well, they've got a point if programmers are the only people who look at the products written in the language. But the Eiffel language has to support the Eiffel method through all phases of development for all interested parties, not just programmers. But of course, easily readable code won't do the programmers any harm. Yeah, well, some may perceive it as a threat to job security, but I don't think they have to worry. I remember when it was said that COBOL was so much like written English that it would put the programmers out of business. It didn't. All right, let's move on. One way to compare Eiffel with the UML is by size, and size could be expressed by more than one measure. But no matter how you measure it, one thing is quite clear. In comparison to the unified modeling language, the Eiffel language is pretty small. We saw earlier that UML was a product of combining ideas of a few people, but now is subject to the forces of an entire community, which of course has its advantages. But as such, it tries to address the needs of many development domains, using many techniques that have proved successful in those domains. Getting all these diverse concepts to mesh can be problematic. In an article published in IEEE Computer in early 2006, Robert France and his co-authors note that the size and complexity of UML version 2.0 seems a little disappointing, considering the original motivation to streamline what they call the apparent bloat of previous versions. Eiffel was originally conceived by a single individual who combined a small number of powerful ideas from the fields of computer science and software engineering. In this respect, its size is limited. The Eiffel method, which gives us a recipe for building high-quality software components, has been very stable since 1988, when object-oriented software construction was first published. The foundations of Eiffel are so well anchored that even though the method does not change much, valuable new concepts like design patterns can be represented easily and effectively. Like UML, the Eiffel language has been standardized under ECMA rather than OMG, and is controlled by a not-for-profit consortium. But the goal of the language remains to serve as a notation for the method, so even changes to the language have been relatively few. When you work with UML, you're actually working with a family of related languages, each of which expresses some viewpoint of a model. The UML 2.0 superstructure defines 13 different diagram types. This gives you multiple products which then must be reconciled. With Eiffel, you use one language to express a single model, which gives you one product. But it's a product which can be viewed from more than one viewpoint. So if Eiffel is significantly smaller than UML, does that mean that it is significantly more limited? Well, the answer is yes and no. Certainly there are things that you can do. That is, there are types of notation that you can use in UML that are not available in Eiffel. But those capabilities that are directly available in the UML but not in Eiffel usually fall into one of two categories. One, those concepts that Eiffel supports just by some different means. And two, those that are not part of the Eiffel method because either they are limiting to the goals of the method or they are simply inconsistent with the method. When we ask some of our customers those customers whose teams had built large Eiffel systems solving complex problems, whether they used UML as a notation in any part of their software development process, they all said that they did not, that Eiffel is sufficient. So Eiffel is relatively simple, but is also highly scalable and capable of being applied in diverse domains. Once again, mostly the things that are available as part of UML but not available in Eiffel are either done some other way in Eiffel or are not compatible with either object orientation or with the goals of the Eiffel method. Let's take a look at an example of each. We'll consider UML's support for state machine diagramming and for use cases. Graphical state machine diagramming is a part of the UML, but it's not part of Eiffel. Still, in Eiffel, object state and how state is affected by behavior are clearly and actively depicted through design by contract. Use case diagramming is part of the UML, but it's not part of Eiffel. This is because during analysis and design, use cases can work against the goals of object-oriented development. So let's have a closer look at those arguments. First, we'll cover use cases, and then we'll tackle state diagrams. Ivar Jakobsen made use cases a popular part of modern development with his 1992 book, Object-Oriented Software Engineering, a Use Case-Driven Approach. Alistair Coburn established himself as an important source of knowledge on the subject with articles published in the late 1990s and his year 2000 book, Writing Effective Use Cases. But the roots of use cases have been around for a long time. Prior to the definition of use cases, some developers relied on a technique called scenarios. A scenario is just a story about how a user interacts with a system. Often these were text-based, something like, a user goes to the automated teller machine and inserts a card. The ATM reads the card's account number and displays a prompt asking the user to enter his or her personal identification number. The user enters the PIN and the ATM looks it up in the database, and so on. You get the idea. Well, today the apparent consensus definition of a use case is that it's a set of scenarios all based on a common goal. So the goal might be that the user wants to get some cash out of the ATM. So one scenario would be the one in which the user quickly and successfully convinces the ATM to dispense the desired amount of cash and walks away happy, wallet bulging. But there might be several other scenarios in which the goal of the use case is not met or only gets met after a little wrangling, like the user's card is not readable by the ATM, or the user forgets or miskeys the PIN. All this is done, of course, to help understand and record how a system is used by those who use it. From this understanding, requirements for a software system are created. In the parlance of use cases, users are called actors. The UML superstructure specification defines how to show use cases and the actors that use them, but it doesn't really say much about what goes into a use case, except to say that the scenarios would probably be depicted using interaction-type notation. So why don't we see use cases in the Eiffel method? Use cases may be reasonably effective, but they're not very object-oriented. They fall into that category of facilities that are available in UML, but are not available in Eiffel because they are not compatible with true object-oriented analysis and design. Here's why. Well, first, by their very nature, use cases and scenarios impose an ordering of operations. The system does function A, then function B. But this is not good for object-oriented development. To get the most benefit from OO, we don't do things this way. Instead, we ask, for some abstraction X, what are the services that instances of X provide, and what are the constraints for those services? This approach emphasizes autonomy versus dependence, and that in turn fosters more flexible, reusable software components. To add to this, there's a clear risk that dependence upon use cases will lead programmers to backslide into functional design. And it's no wonder, because use cases focus on the functional programming approach of what the system does, rather than the object-oriented approach of what it does it to. So employing use cases, particularly by those not highly experienced in object-oriented development, may cause a resurrection of some of the exact problems that OO was conceived to prevent. Another problem with using use cases early in the life cycle is that they are based on a view of a system that does not yet exist. So the analysis and design decisions that are made based on use cases can dictate a final solution that's no better than the initial vision that created the use cases. With more purely object-oriented analysis and design, abstractions are identified and then reified into classes. The classes are fleshed out with services and their contracts. So the resulting system may very likely evolve into something far superior to anything that was envisioned in the early stages of the project. But these arguments shouldn't be taken to mean that use cases are a bad idea. Although they aren't prescribed by the Eiffel method, use cases could prove to be a very helpful tool in the quality assurance stages of a project. Okay, on to state machine diagramming. State machine diagramming falls into the category of facilities that are provided as part of UML but are not included as part of Eiffel because Eiffel uses other means to achieve the same goal, in this case to depict object state and to record allowable changes to that state. Before we get started with an example that I hope will help you understand this, let me give you a couple of cautions. First, the object of this example is to show that although the Eiffel method and notation does not employ state machine diagramming as a graphical tool, object states and transitions are specified clearly with the Eiffel notation. To do this, though, we rely fairly heavily on Eiffel's design by contract facility. I don't have time to explain design by contract here, so if I begin to sound like I'm spouting total gibberish, then you might want to skip this example for the time being and come back to it after you've viewed the design by contract presentations. Secondly, I want to say that state machine diagramming is an analysis and design tool. It's included in the UML because it has demonstrated value for helping to understand problem domains and to design software solutions. Well, Eiffel is an analysis and design tool too. But that doesn't mean that if you model the same problem using state machines and using Eiffel, that in the end you would have built two identical software products. My point here is that I'm trying to demonstrate for this particular example how states and transitions are naturally specified with Eiffel without making the state machine itself part of the problem domain. But if you do end up working with a problem that requires complex state machine modeling, it may be appropriate to model the machine as such. And I think you would be well advised to have a look at the state pattern in the book Design Patterns by Gamma, Helm, Johnson, and Vlissides. Then, if you want to see how that design pattern can be implemented in Eiffel with design by contract, refer to Design Patterns and Contracts by Jezekiel Train and Mingens. Both of these books are published by Addison Wesley. Okay, all the disclaimers are out of the way now. Let's get started. Different types of state machines have been used for a long time for language processing and compiler construction, real-time and communication problems, and have value in other areas of computing as well, such as specifying complex graphical user interfaces. Still, many programmers have never been put in a situation in which modeling with state machines was actually necessary. On his Agile Modeling website, Scott Ambler estimates that at most, about 5% of business classes have the type and degree of complexity necessary to warrant using state machine diagramming. So it's not a need that us garden variety IT folks run into very often. The type of state machine diagramming provided as part of the UML is an object-oriented variant of the Harrell state chart, formalized by David Harrell, by the way, another name worth Googling. Alright, for our demonstration, let's use a simplified example of an organization, like Eiffel Software, that offers certain training courses. If we want to model the offering of a particular course, some things might immediately present themselves as abstractions in the model. Specifically, a course would represent some specific course like hands-on object-oriented software construction. When a course is offered, it is offered at a specific facility, a venue, at some specific starting date, to a set of enrolled students. So we might want to model a course offering as a one-time offering of some specific course at some specific venue with some specific starting date. Students enroll in the course offering. Any particular course would have a maximum enrollment, which would be the largest number of students to which that course could be taught effectively. So as we record this analysis information in Eiffel, it would suggest a course offering class, with features something like this. We see the course to be taught, the venue, the starting date, and the list of enrolled students. Let's use a state machine diagram to record an understanding of how changes in a course offering's state occur based on stimuli. We might think of an instance of course offering, once it's been properly created, as existing always in one of four distinct states. Here you see them in UML-style rounded corner boxes. Now let's examine the meaning of the states and see one way we might represent that meaning in Eiffel. After creation at runtime, an instance of course offering is complete with an associated course, a venue, a start date, and an empty list of students. And the instance begins life in a state called enrolling. We can show that this is guaranteed by looking at the post condition on our creation procedure. Remember now that in Eiffel, creation procedures are somewhat like constructors in Java or C#. The assertions you see following the ensure keyword are guaranteed to be true after the procedure completes. The first four lines just ensure us that the attributes for the instance will be properly initialized. But look at the line labeled enrolling. It is a simple assertion, is enrolling. Is enrolling is a Boolean query on instances of our class that, when true, indicates that an instance is in the state of enrolling. Okay, but what exactly does enrolling mean? Well, at the simplest level, because we decided that the operation of our course offering is deterministic with mutually exclusive states, we can say that it means this. If a course offering is in the state of enrolling, then it has been properly created, and it is neither full, nor is it closed, nor is it canceled. And we can guarantee mutual exclusion of states with a simple assertion in the class invariant. This will make sure that we know about it immediately if any instance ever attempts to be in more than one state at a time. But enrolling also carries the meaning that students are allowed to enroll because there are still openings in the class. We can express this by defining enrolling, again in the class invariant, like this. So students can continue to enroll as long as there are slots available in the course offering. That is, as long as the current number of participants is less than the course's maximum allowed. Once the last slot is filled, then the course offering becomes full. Of course, that means that we can put a definition for full in the invariant too. It would look like this. So when the course offering is full, the number of participants is equal to the maximum allowed by the course. In the state machine model, we would represent the event of a student enrolling as a transition from the enrolling state and either back to the enrolling state or to the full state. But here it looks like an enrolling student could cause a non-deterministic transition to both enrolling and full. UML gives us the capability to distinguish between which of these transitions can occur for a particular enrollment event. We can put a guard condition on the transition. The guard condition must be true in order for the transition to take place. So let's add guards to these transitions. If a student enrolls and will take the last slot available, then the transition to full can take place. If there is more than one empty slot, the transition back to enrolling is allowed. When you specify this in Eiffel, it's not really necessary to make that distinction, simply because, as we saw earlier, the number of students enrolled is part of the definition of the course offering state. It's necessary only to ensure that the feature that enrolls students is called only while the course offering is enrolling, and that afterwards it has transitioned into one of the two valid states. So the contract for course offering's enroll procedure looks like this. The precondition, following the require keyword, includes an assertion to make sure that the course offering is currently in the state of enrolling, and also one to make sure that the argument is valid. Then, after the student is enrolled, the postcondition includes an assertion that ensures that the student is among the enrolled participants, and another to make sure that the course offering is still enrolling or is now full. Let's quickly consider the states closed and canceled. At some point, whether the course offering is still enrolling or is full, the deadline for enrollment will pass, and the administrator will close the course offering to further enrollments. Also, at any time and from any other state, a course offering could be canceled for any of a variety of reasons. We'll assume that once canceled, a course offering is no longer sensitive to any event. Now, if you're willing to bear with me just a little longer, let's consider what happens when a student withdraws. This could happen if the course offering is enrolling, full, or closed. In the cases of enrolling and closed, the event leaves the course offering in that same state that it was before the event. But in the case of a full course offering, withdrawing a student frees up a slot allowing a new enrollment. So there's a transition from full back to enrolling. So let's see how this gets specified in the postcondition of the course offering's withdrawal procedure. The first assertion just makes sure that the student in question is no longer enrolled. The second and third guarantee that if the course offering was either enrolling or closed, then it will be in that same state after the withdrawal. And the last assertion ensures that if the course offering was full at the time a student withdrew, then it will be able to enroll at least one student again afterwards. Okay, well, thanks for your attention in this somewhat lengthy example. I hope you've begun to see now that because of design by contract, object state and how it changes are integral parts of Eiffel development. As you go through analysis and design, you record in Eiffel information about the valid states and transitions that affect objects in your problem domain. So for most problems, it wouldn't be necessary to do any diagramming. You just build the Eiffel, and that Eiffel eventually becomes your completed software product. Well, now that we've seen some ways in which Eiffel and UML differ, let's look at one way in which they're a lot alike. Earlier I said that many developers never find it necessary to use more than a small set of the UML's full offerings. Well, in a lot of these cases, the real workhorse of the UML is the class diagramming notation. Class diagrams allow the representation of the essentials of object-oriented architecture: classes, their features, and their relationships with other classes. Martin Fowler, in his book UML Distilled, says that if someone approached you in a dark alley offering to give you a peek at a UML diagram, chances are good that it would be a class diagram. As a consultant, the majority of the UML diagrams he sees are class diagrams. Although UML's class diagramming capability differs some from Eiffel's, they do have a lot in common. Let's look at an example of a class diagram in UML. We'll do a class diagram of the course offering example that we showed with the state machine diagram, except that I've added an additional class, training product, so that we can show a generalization or inheritance link. Here's the class diagram that includes course offering. Now, if you're a 32nd degree UML wizard and you see something that offends you in my UML, I hope you'll just consider it a rookie error on my part and try to focus on the spirit of the example. Email me if you'd like and I'll try to fix it. Okay, we'll be looking at the same example in Eiffel notation in a minute, so let me point out some areas of interest so that we can look at the similarities and differences. You see the class course offering. It has a direct relationship with course, date, venue, and student. Notice that the link between course and training product has an arrow with an open triangle head. This indicates that training product is a more general notion and course is a more specialized one, the inheritance relationship in object-oriented software. Also notice that the relationships between course offering and course, date, venue, and student are all UML associations. The arrowheads show navigability from course offering to these properties. For these associations, navigation in the other direction is not defined. When we look at the Eiffel version, you'll see arrowheads there too, but we tend to think of them as indicating direction of dependency, though they also show navigability. Another thing to notice is the multiplicity on the associations. A valid course offering will be associated with exactly one course, venue, and date, but it may be associated with a number of students. The valid ranges from 0 through the maximum number allowed by the course. These UML properties could be shown in the notation also as UML attributes, that is, as line items within the class box rather than as associations. Here's the course offering with the attributes instead of the associations. It's really very nearly the exact same information, just a different way of showing it. You'll see that we can do a very similar thing in Eiffel. Notice that these attributes all have public visibility, as denoted by the plus sign preceding each. With all that in mind, let's take a look at the same example diagrammed in Eiffel. The graphical notation most commonly used to build class diagrams by Eiffel developers and tools is called BON, B-O-N. BON is an acronym for Business Object Notation. This notation was developed in the late 80s and early 90s and formalized in 1995 in a book by Walden and Nerson called Seamless Object-Oriented Software Architecture. The class diagram you see here comes from a screenshot from Eiffel Studio. Eiffel Studio uses BON to provide graphical views of related classes in Eiffel. In this case, the classes in our course offering example. Notice first the classes, represented by ovals, are grouped in two rounded corner dotted line rectangles. The rectangles indicate the cluster to which these classes belong. If you're familiar with the UML notion of packages, you can think of clusters in somewhat the same sense. They give us a way to group elements, classes in the case of Eiffel clusters. One notable difference is that the package also implies a namespace for its members, whereas clusters do not. So all the classes relating to the training products are in the cluster with that same name. But the date class comes from the time cluster, which is a vendor-supplied library. Of course, there are many more classes in the time cluster, but we aren't showing them in this view because they aren't directly related to the course offering class. You see that there are two different types of arrows here, double line green arrows and single line red arrows. Each of these arrow types represents one of the two valid relationships between classes in object-oriented software, client-supplier and inheritance. So, for example, a relationship between course and training product is inheritance. A course is a specialization of training product. The relationship between course offering and course is client-supplier. Course offering has or uses an instance of course called associated course. Therefore, class course offering is a client to services supplied by class course. Of course, these relationships are analogous to UML's generalization and association. The client-supplier links are labeled with feature name in the client class that manifests the relationship. Now let's look at the relationship between course offering and student, because it's a little different from the others. Each course can have a number of students. The label on this relationship shows that although course offering is a client to student, that the students in question are managed in a list. List is a generic class, and student is an actual generic parameter to the list class. That is, it says what types of things are being kept in the list. So really, course offering is a client to the list class as well. And we could ask Eiffel Studio to show us that relationship if it were appropriate to the purpose of the view. When we looked at the UML version, we saw how the properties could be expressed as attributes in the class box. In Eiffel, you have the option to view these relationships as a portion of the interface of course offering. If you select the contract view in Eiffel Studio, you'll see the relationships in lines of text similar to the UML attributes. Now, there's still a couple of things we saw in the UML diagram that we haven't seen here yet. One of these is visibility. Remember how the plus sign preceding the attributes in the UML diagram meant that they were publicly visible. Well, all these features in the Eiffel diagram are publicly visible too. You can tell that by the feature clause that contains them. In this case, the feature keyword is followed by the class name any in braces. This means that the features that follow are accessible to class any and all classes which inherit from class any. And because all classes inherit from class any, that means that the features are essentially public. So the way that you control access to features in Eiffel is by naming a class or list of classes in the feature clause, and this gives you very fine-grained control. Another thing that we need to talk about is multiplicity. Let's look at associated course. Associated course is a single declaration of type course. So from course offerings viewpoint, a single course offering will be associated with a single course. The same applies to schedule venue and start date, but not so for participants. Participants is a list of students, so the list can contain any number of students. But we know that there's a multiplicity constraint for the number of students based on the maximum defined by the course. Where do we see this? In the class invariant, of course. Remember, the class invariant is a statement of what it means for instances of a class to be valid, and the multiplicity constraint is an issue of validity. So here's an assertion from course offerings class invariant. It shows that the number of participants must always be less than or equal to the maximum allowed by the associated course. Now you might be thinking, but don't we need to ensure too that the number of participants is never negative? Well, that is a good question, and it's got an even better answer. Participants is a list of students. List is a high-quality, reusable software component from the Eiffel-based library. If we looked at its specification, and we should do so before we try to reuse it, we would see that there's an assertion in list class invariant that guarantees count can never be negative. So there's no need for us to repeat that. Okay, I hope you see now that although there are differences in the way class diagrams are rendered between UML and Eiffel, there's also a lot of common ground in the types of information that they can convey. But you should always remember that a class diagram built in Eiffel Studio is different from a UML class diagram in one very important way. It's a view of existing software elements. So say I add another client-supplier link graphically to course offering. That's the same as typing in a new declaration in the text of the class. It's just different views of a single product. Alright, well let's wrap this thing up. The U in UML stands for unified, showing that it's a notation formed out of an amalgam of ideas from many sources. But the U could stand for universal, because it attempts to provide facilities for a multitude of specialized development needs. And indeed, the U could stand for ubiquitous, because it has become the most used notation for software development today. Even UML's most ardent supporters would have to admit that taken as a whole, the UML is pretty big and daunting. Fortunately, most users only need small portions of the UML to do their day-to-day tasks. UML's size and diversity make it difficult to integrate everything in a consistent way. Although it's claimed that UML is platform independent, we see some evidence to the contrary. There are areas in the notation that seem to mimic the restrictions of certain target programming languages, particularly Java, C#, C++. For example, the kinds of visibility applicable to UML elements use a coarse-grained terminology inspired by those languages, public, protected, private, package, rather than a finer-grained approach based on sets of classes as in Eiffel. Another example is the explicit support for the notion of interface and interface implementation as known in C# and Java. With quality multiple inheritance as in Eiffel, it would be unnecessary to support a separate interface entity. Instead, the term interface could be used in a more pure form, that is, the definition of services available to clients of a class. Rather than being first a notation, Eiffel is first a development method focusing on software quality. The method is supported by a notation, the Eiffel language, which has multiple views, textual and graphical. Eiffel is much smaller than the UML, and because the notation is compilable, it's inherently consistent. Eiffel scales well and is suitable for small development efforts and large. Because every development phase is documented in the same language, the method is seamless and easily reversible. And to add the icing to the cake, Eiffel is committed to pure object technology with support for genericity, safe and controllable multiple inheritance, and design by contract. Well, that's about it. There's only one more slide, just some links you may find interesting. Thanks for taking the time to view this presentation. I hope you found it both enjoyable and informative. I also hope you'll continue to learn about Eiffel and download one of our free versions and give it a try. Until next time, thanks again.